Hi everyone, my name is Rafael and I'm going to be talking about unprovable security of leakage resilient cryptography beyond the information theoretic limit. So what is leakage resilient cryptography? Well, as the name suggests, it's a study of cryptography in the presence of leakage. Our focus today will be on what's referred to as the bounded leakage model. So in this model, the attacker will get to see some arbitrary polynomial computable leakage on the sequence of participants. The only restriction is that the length of the leakage is of some a priori bounded size. In this case, we're going to call the leakage bound L. And clearly, the length of leakage needs to be much shorter than the secret, or otherwise, of course, if you leak the whole secret, no security can be achieved. So let us focus on the simplest and perhaps the most fundamental task in crypto, that of a one-way function, and let us focus on the task of L leakage resilient one-way functions. And we can specify this as a security game between a challenger and attacker. It proceeds in the beginning just like the normal one-way function security game. So the challenger samples some input x, some random string x, and sends y equals f of x to the attacker. The attacker's job is to find a pre-image to f of x. But in contrast to the standard game, the attacker now gets to also ask the challenger for some leakage on the secret x. And he does so by specifying a leakage query, which is just a circuit. So let's say it specifies a circuit Q1. And then he will get back the evaluation of the circuit on the secret x. And he can specify another one, and it continues for a while. At the end of which, the job of the attacker, as we said, is to output some pre-image x prime, such that f of x equals f of x prime. So it's a pre-image to f of x. We say the attacker wins if indeed it manages to output a good pre-image. And additionally, the total length of the leakage seen by the attacker on the secret x should be smaller than L of n. In other words, the attacker managed to invert while at the same time using L-bounded leakage. So what's known about leakage resilient one-way functions? Well, the first observation that can be made is that any one-way function or any one permutation is leakage resilient up to log n bits of leakage. And this simply follows from the fact that if I give you log n bits of leakage, that's something you could have just guessed with probability 1 over n. And so therefore, that will just result in a polynomial security loss. In fact, by the same argument, any sub-exponentially secure one-way function or one-way permutation is leakage resilient up to n to the epsilon bits of leakage, simply because the fact that even n to the epsilon bits, you can guess correctly with probability 2 to the minus n to the epsilon. So if you have security that is much bigger than that, or if you're secure against 2 to the n to the epsilon attackers, then even after the security loss, you still have security. Now, can we go beyond these type of trivial leakage resilience? And indeed, there's a huge body of literature on leakage resilient cryptography. And in particular, for the case of leakage resilient one-way functions, the following very beautiful result can be shown, and was shown by Katz and Vaikuntanathan and Alben Dodis Vix in 2009. And it's the fact that any sufficiently compressing collision resistant hash function turns out to be very, very leakage resilient, even up to n over 2 bits of leakage. Let me briefly recall the proof idea because it will guide us towards the problems that we're going to be looking at. So consider some hash function that's very compressing and is also collision resistant. Now, the key observation is that if I give you h of x, since h is so compressing, and you take a long string x and compress it to something small, given h of x, x still has a lot of entropy left in it. In fact, even if I give you h of x and some leakage on x, as long as this leakage is small, there is still a lot of entropy left in x. So what this means is that if we have some attacker that given x and h of x finds a pre-image to this function h of x, it's very unlikely to be the actual x because x has so much entropy in it, right? In other words, any attacker that succeeds in inverting this function h, even given a leakage, can now be used to find a pre-image x prime that's different from an original pre-image x that I'm starting off with. In other words, I can use this attacker to find a pair, X and X prime, that map to the same output, therefore we find a collision. I maybe went over that argument a little bit fast, but the key point that I want you to remember is that in order to go through with this proof, it's very important that the secret X has actual entropy left, and in fact, a lot of it, even after leakage. And this principle turns out to be kind of universal in the proofs that we use in order to prove leakage resilience beyond this type of trivial bounds. The above mentioned trivial bounds, this log-L bounds. And the focus of this paper is, can we go beyond this type of information theoretic barrier? Can we go beyond leakage resilience of secrets that are information theoretically hidden? In other words, can we also prove leakage resilience for secrets that are just computationally hidden? In other words, they are information theoretically determined, but computationally, they have maybe some entropy in them. In particular, what if we focus on one-way permutations? As I mentioned, any sub-exponential secure one-way permutation is leakage resilient. But what if I would like to base the existence of leakage resilient one-way permutation on a polynomial hardness assumption? Is that something we can do? Right. Note that a one-way permutation completely, the output of a one-way permutation completely determines the secret X. Right. There is no entropy left at all. So it really doesn't fall into the framework that we know for which we know how to prove things about. Now, in a one permutation, the output fully determines it. What if we relax a little bit more? Now, what if I allow you to construct a one-way function? It doesn't have to be a permutation, but what if I restrict you to constructing one-way function where the number of pre-images is smaller than 2 to the n to the epsilon, and you still need to get n to the epsilon leakage resilience. So now the output of the one-way function itself does not determine X, right? So you might have 2 to the n to the epsilon pre-images, so there might be a lot of entropy left. But after n to the epsilon bits of leakage, now that suffices to determine the X. So this is the second question, really gets us exactly to the border of kind of the information theoretic limit, right? So the output of the function itself plus the leakage determines it, and just barely determines it. So our main result shows that the answer actually is no if you restrict to black box security reductions from what's referred to as constant run interactability assumptions. I'll tell you shortly what a constant run interactability assumption is. And a little bit more precisely, what we show is that any black box security reduction from such an assumption must itself constitute an attack on the assumption. So if you manage to prove leakage resilience, for instance, of one permutation, n to the epsilon leakage resilience of one permutations, and you base it on some constant run assumption, in fact, the reduction can be used to break the assumption on its own. All right, so what's a constant run interactability assumption? So following a long line of work started with Naor, we're going to be modeling an interactability assumption as an interaction between a challenger and attacker, much as in the same way as we defined leakage resilient one-way functions. So let's consider, for instance, the most basic assumption, the factor assumption. That can easily be modeled as a security game where the challenger samples P and Q, gives the product to attacker. Attacker's job is to find P and Q given the product n. An attacker is said to succeed if he managed to get the challenger to be happy to output 1. A little bit more formally, an interactability assumption consists of a pair, C, T, and intuitively correspond to the assumption that no PPT can make C output 1 with probability significantly higher than T. Now, the above type of factoring assumption is what we refer to as a 2-round assumption, but we can consider interaction between C and A that proceeds in more rounds, and we refer to those as R-round assumptions. So 2-round assumptions capture things like factoring, or that F is a one-way function, and so on and so forth. Constant run assumption capture things like the assumption that an encryption scheme is semantically secure, or that some interactive protocol, some constant run interactive protocol is witness hiding, etc. We can consider, in fact, things that are not constant round, let's say an L1 assumption, can be used to capture exactly the assumption that a particular function f is L leakage resilient. Right? If you remember the way I defined leakage resilience, it really corresponds to, it's exactly an L-round assumption in this framework. All right, so what's our main theorem? Our main theorem is the following. Assume the existence of collision-resistant hash functions and consider any function f where any value y in the range of this one function has at most 2 to the n to the epsilon number of preimages. So in particular, this function has now what we refer to as a bounded preimage set sizes, 2 to the n to the epsilon bounded preimage set sizes. And let CT be any constant round intractability assumption. What we show is that any reduction R, any black box reduction R, for basing n to the epsilon leakage resilience, one wayness of F on the hardness of C, if there exists such a reduction, any black box reduction, then this reduction can actually be used to break the assumption itself. Okay, so I'll get shortly to what I mean by a black box reduction. Let me, before going there, let me make a few remarks. First of all, our result is actually more general. It refers not just to one-way functions, but also applies to a more general notion of leakage resilience of NP search problems. And in fact, it applies even to the worst case scenarios of NP search problems. Let me also mention some related work. First of all, Daniel Vix shows a very nice and related black box impossibility result for one-way permutations. The difference is that his result only applies to restricted classes of black box reductions, in particular black box reductions that treat the leakage query also as a black box. In contrast, our results work for all black box reductions, and in particular those that may access the code of the leakage circuit in a non-black box way. And in recent years, it's been shown that these type of non-black box uses of leakage queries can be quite powerful, and indeed are constructions that leverages. Another related work is one by Agarwal and Maurer. They also study a notion of leakage resilience of NP search problems. They don't present any lower bounds of black box separations, but instead relate this problem to some other computational problems. Finally, there's a large body of literature on what's referred to as meta reductions, and meta reductions is this very nice technique for proving the types of black box separations as we're doing. And in particular, this is the way the meta reduction approach works. So let's say we have some black box reduction R, and we'd like to prove that any such black box reduction R should be possible in the sense that the existence of such a reduction can be used to break the assumption on its own. So this is how we do it. We design one particular attacker A that's going to break the purported security of the scheme we're interested in. In our context, we're going to consider some attacker A that's going to be breaking leakage resilience of some purported leakage resilient one function. And next, we'll show some method for efficiently emulating this attacker in polynomial time. So we're getting rid of this thing. And what that shows is that any such black box reduction now can therefore be used to break C in polynomial time, because this inefficient attacker is not really needed. All right, so today we're going to apply this method for leakage resilient one functions. And for simplicity, I'm going to focus my attention on one-way permutations. So the first thing we need to do is to exhibit this attacker A, and the next step will be to show how to get rid of it, how to emulate it. So remember, we're going to be considering some attacker A that is supposed to break leakage resilience of some one-way permutation. So what will this attacker do? The attacker, given some value y equals f of x, is going to now be requesting some leakage. And after it sees the leakage, it will be breaking this one-way function. So what is the leakage it's going to be requesting? Well, it's going to be requesting to hear a succinct argument of knowledge of the statement that there exists some x such as f(x) equals y. Okay. So how can it ask the reduction to provide such a succinct argument of knowledge? Well, first of all, we do know that based on the existence of collision-resistant hash functions, using Kilian's argument, we can get a succinct argument of knowledge. So by succinct, I here mean that the communication complexity of this argument of knowledge is small, let's say n to the epsilon. So any succinct argument has the property that the length of the prover messages are short. So in principle, we can think of this as leakage. The question is, how does the attacker ask the reduction to provide this proof? Well, the point is that the prover in non-succinct arguments, in particular Kilian's argument, is deterministic. So really, the prover messages can just be viewed as some very specific types of leakage, right? In particular, the prover's next message function is the type of leakage queries the attacker could ask for in order to hear this, get this succinct argument of knowledge from the reduction. Okay, so the attacker can now, as we've seen, can request from the reduction to hear the succinct argument that the reduction knows some f(x), some pre-match x, such as f(x) equals y. If this argument is accepting, the reduction will now in brute force in exponential time find some x such as f(x) equals y and return it to reduction. So pictorially, the reduction sends some y equals f(x). Next, the attacker is requesting to hear this succinct argument. And finally, if this argument is accepting, then it returns x. So what's the intuition for asking the attacker, asking the reduction to provide a succinct argument? Well, let's see what happens when the attacker is providing the succinct, when the reduction is providing the succinct argument. The reduction is proving to the attacker that it knows a pre-image to y, right? So it must actually know some x such as f(x) equals to y. And it's only then that the attacker is willing to give him this pre-image. But if the reduction knows x, it really doesn't need the attacker, right? It could have just emulated this attacker on its own by just getting rid of it and just outputting x to itself. Okay, we'll see shortly how to provide this emulation and getting rid of this attacker. But before I do that, let me just mention that a similar technique of using succinct arguments in the context of proving impossibility results were actually used in two very nice works in the context of leakage resilient zero knowledge and secure computation. All right, so now let me return to how we can actually formalize this idea that this attacker is not really needed. And that is very easy. We can fully get rid of this attacker by honestly emulating the role of the attacker up until the point where the attacker is supposed to provide this pre-match x prime. But now, instead of in brute force finding this pre-match x prime, we will just rewind the reduction and provide some new challengers in this argument of knowledge, to extract out an x prime from the reduction. And such an extraction should succeed because this is a good proof of knowledge, an argument of knowledge. And once we have that, we just give it back to reduction. So now we've seen that, in fact, this particular attacker, which is a valid attacker, can also be removed. We can just emulate it for the reduction on its own, and we're done. Well, not quite so fast. Turns out that there is a subtlety. So we haven't really argued that this emulation generates the same distribution as the real attacker. And that's actually very important. But it turns out it does. So since f is a one representation, it turns out that this x prime that we're extracting from the reduction must actually be equal to the x that the attacker would have returned. Remember, the attacker is finding this x using brute force. But since it's a one representation, there is exactly one pre-image, right? There can only be one, and therefore, the one we're extracting must be the same as the one that the attacker found in using brute force. Note that this argument fails if we're talking about a general one-way function. In fact, even if there just has more than one pre-image, we're not sure that we're finding the same one. But as I mentioned, there are ways that you can extend this argument to work even if there are more preimages, as long as they're bounded, but it requires changing the argument quite a bit. In fact, there is another issue. In the picture in the previous slide, we actually implicitly assume that the reduction is very well behaved. It only talks to the attacker once, and it just talks to it once, and it doesn't rewind the attacker. Really, in practice, black box reductions, they can do many more crazy things. Often black box reductions actually don't run just attacker once, and typically they rewind the attacker. They may also nest many different executions with attacker in some bizarre ways. And so in this picture here, we're showing one particular way of nesting interactions with attacker. And it turns out that if you would like to do the same type of rewinding the way we did in order to extract out these preimages, if the attacker nests these executions in this particular way, then that will just result in a blow up in the running time, and this extraction is going to run in exponential time. I won't go into details on this thing, but it's related to problems similar to those arising in the context of concurrent zero knowledge. Luckily for us, this problem is not new and arose already in earlier works, particularly in a work of mine from almost 10 years ago. We developed some techniques for overcoming exactly this issue, and it relies on doing two things. The first thing is that we can't just rely on any type of argument of knowledge, but rather we need to rely on a more restricted class of arguments of knowledge, something called special sound proofs, and some generalizations thereof. And the complication that arises now is that, unfortunately, we're not aware of any special sound succinct arguments of knowledge. However, if we observe the problem that we have here, we actually don't really need a protocol that's fully succinct in the sense that the communication complexity is short. Rather, the only thing we need is the length of the prover messages are short. The verifier can send long messages, but it's important the prover sends short messages, because it's the prover messages that constitute the leakage. And it turns out that by massaging Kilian's protocol, we can obtain now a laconic prover special sound protocol that will suffice for using the technique in P11. The second thing that we need to do is we need to modify the attacker to not just ask for a single special sound or a single argument of knowledge for this knowledge of the preimage, but rather we require the attacker requires the reduction to provide many sequential arguments of knowledge. And it's only after hearing all of the sequential proofs of knowledge and all of them being accepting that the attacker is going to respond with a preimage. Again, I won't go into detail why this is needed, but intuitively, in order to prevent these type of nesting problems like we had on the on slide here, if we have many sequential proofs, we can cleverly figure out which ones to rewind from in order to extract out the preimage without running into this overhead in running time. So summarizing what we've shown here, or what I sketched in the proof of, is that assuming existence of collisions in hash functions, if you take any one-way permutation and any constant running interactability assumption, then we have the following. Any probabilistic polynomial time black box reduction R for basing n to the epsilon leakage resilience of F on the hardness of CT can be used in order to get some other probabilistic polynomial time attacker B that just breaks this assumption on its own without any help. So if you can base n to epsilon leakage resilience on one permutation on the hardness of this constant run assumption, in that case, the assumption must be broken in polynomial time. As I mentioned, this type of approach here only works for one permutations, but using some additional ideas, we can extend it to work not just for one-way permutations, but also for one-way functions with a bounded number of preimages. And in order to do this, it's very important that the number of preimages is sufficiently small so that the leakage, so that the output of the function together with the leakage suffices for information theoretically determine the preimage. And if so, the impossibility result still holds, and thus we get the final main theorem. And that is it. Thank you very much.